Good morning. I'm Mofokeng from South Africa. It's a great pleasure to present at the first International Online Conference on Nanoscience and Technology 2018, which is presented by Africa Grofin. I'm a PhD student at the University of South Africa, and my research focuses on phosphors for solar cells, and this presentation will be more on properties of up-converted luminescence materials for solar cells application. During the course of my presentation, I will start with motivation and background for renewable energy and go all the way to summary and conclusion of my presentation. The aim of this research is to enhance the efficiency of solar cells by incorporating up-converting luminescent material, which is zinc titanate co-doped with YBS, a sensitizer and a suitable activator. This luminescent material will convert the electromagnetic waves that are not absorbable by a solar cell into wave ranges that can be absorbable by solar cells. Why? Because energy demand remains one of the world's greatest challenges. So technology in many different solar cells is considered as an alternative for producing electricity, as they produce electricity from sunlight without any green gas emission. This research is focusing on photovoltaic cells, specifically dye-sensitized solar cells. Figure 1 here shows a typical diagram for a solar cell, and we can see that it uses energy from the sun and convert it into electricity. But some of this energy from the sun is not absorbed to smaller energy photons that are transparent to the semiconductors, and excess of higher energy photons of semiconductor is lost to lattice thermalization. According to literature, this energy loss can add up to more than 50% of utilizable solar energy for solar cells. Introducing phosphors for up and down conversion of photon energy in dye-sensitized solar cell is a recent research focus into reducing the energy loss. Up and down conversion are one of the promising methods to overcome problems of transparency and thermalization. In general, up conversion is the absorption of lower energy radiation by a phosphor, which transfer it to higher energy radiation, which may correspond to the visible band, ultraviolet band, etc. Down conversion is the absorption of a higher energy radiation, which is emitted as a lower energy radiation. The composite was synthesized using the solid-state chemical reaction method. The study materials were commercial zinc oxide, titanium dioxide, and ABM acetate hydrate. During the preparation, the stoichiometric amount were first mixed into slurry using ethanol inside a glass beaker at room temperature. The slurry was dried inside an oven at 120 degrees Celsius for 2 hours, then annealed at 1100 degrees Celsius for 4 hours inside a furnace. Then the resulting white composite phosphor was ground gently using a pestle and mortar. From the crystal structure and morphological analysis, the XRD patterns of the undoped and ER-doped composite show diffraction peaks corresponding to the crystal planes of hexagonal zinc titanate and spinel zinc titanate faces. The formation of rutile in this case is due to the decomposition of perovskite zinc titanate when the prepared samples were annealed at higher temperature. The morphology of the prepared sample consists of agglomeration of faceted spheres and hexagons. Consistent with XRD data, the SCM image have shown that doping with ER did not change the crystal morphology since the XRD patterns of the two materials are the same. The spectra shown in this case show an intense UV absorption band below 400 nanometer due to band-to-band absorption. In addition to that, there are 4 absorption bands in the visible and near-infrared spectral region corresponding to transitions of ER ions. The insert in this figure shows the estimated band gap from the Tox relation of the two samples, and it was approximately 3.67 and 3.7 electron volts. The up-conversion emission spectrum of composite phosphor was measured using a 980 nanometer diode laser. The resulting emission spectrum with peaks in the visible range of the electromagnetic spectrum indicating successful up-conversion of the near-infrared photon energies. The displayed green emission position from 514 to 574 nanometer and the red emission position from 640 to 690 nanometer correspond to the transitions of ER ions. The CIE diagram suggests that the observed emission resembles a greenish yellow color. The diagram here shows the energy level diagram for up-conversion emission of ER ions. Under the excitation of 980 nanometer, ER ions at the ground state, which is 4I152, were initially excited to the 4I112 state through ground state absorption process. The ER ions located at this state are promoted to the highest intermediate, which is 4F72 state of ER through excited state absorption. Then the ions relax non-radiatively to different state of ER ions followed by radiative relaxation decay corresponding to green and red emissions. This mechanism also shows the splitting of radiative relaxation for red emission as shown in 2 from the previous slide. So the number of photons involved in the mechanism of up conversion under 980 nanometer excitation can be determined from the double log plot of power dependence of up conversion luminescence intensity. So the estimated values from the slopes of this plot are approximately 1.8 and 1.7 for green and red emission. And these excitation photons indicate that a double photon mechanism was involved in the up-converted luminescence of ER ions. In summary and conclusion, ER-doped composite phosphor was successfully synthesized using solid-state chemical reaction at 1100 degrees Celsius as proven by XRD patterns. The photons with energies corresponding to the near-infrared emission range were successfully up-converted to photon energies corresponding to the visible emission range under the excitation of 980 nanometer laser diode. The CIE diagram indicates that the overall displayed emission resembled a greenish yellow. Double log plots of the power dependent of luminescence intensity showed that 2 photons contributed to the displayed up-conversion luminescence of the prepared phosphor. Mostly, I would like to thank everyone for taking time to listen to my presentation, and I would like to acknowledge Physics Department from University of South Africa, Department of Science and Technology, and NRF for funding my research. It was a great pleasure to take part in NANO 2018. Thank you.